As I did in the pressures video, moles being proportional to pressures, I'm going to do the same thing here and move this up to make room. Maybe. There we go. Because it turns out the long way to do these problems takes up more space. We're going to start out as we always do for stoichiometry, and we're going to try and get moles. And up here was a shortcut because we knew moles and volumes were going to do the same thing. Down here, though, we're going to pretend we don't know that. We're going to start out turning our volumes and temperatures and pressures into moles. We know PV equals nRT, and we can rearrange that a little bit so that N equals PV over RT. Our moles then of the nitrogen are going to equal the partial pressure of the nitrogen, the volume of the nitrogen over RT. And then our moles of the hydrogen is going to be the partial pressure of the hydrogen, the volume of the hydrogen over RT. And again, the fact that we're doing pressure R and T the same, means eventually we're going to come full circle and not have to have done it at all. Right here, pressure of the nitrogen, 2 atmospheres. Volume of the nitrogen, 6 liters. R is 0.08206 liter atmospheres over moles Kelvin. And T is 298 Kelvin. In this particular case, for the nitrogen, we get 0.491 moles. And as you may recall, that is what we have. For the other one, I'll just change colors a little bit. Still 2 atmospheres, but this time we've got 15 liters. Still 0.08206 liter atmospheres over moles Kelvin. And still 298 Kelvin. We expect this number to be a little bit higher. It ends up 1.23 moles of hydrogen. That is what we have. The stoichiometry is the same as always. Now we have moles. We'll set up a mole ratio based on the balanced chemical equation, which I snuck in right there, but our ratios are a 1, a 3, and a 2. We know then for every 1 mole of nitrogen, there's 3 moles of hydrogen. And we find out that we need, and I'll be a little cleaner with my color coding. For the first one, 1.47 moles of hydrogen, and for the second one, 0.410 moles of nitrogen. And now we can do our comparison to find our limiting and excess reactant. Have 0.49, need 0.41, I have more than I need. That is my excess reactant. Have 1.23, need 1.47, that is the limiting reactant. And you'll notice nitrogen was excess, hydrogen was limiting when we did things the fast way. Once we have this information, we can get our amount excess. That is what we have minus what we need of the excess, so that's 0.491 moles of nitrogen minus our 0.410 moles that we need. And you end up with 0.080 moles of nitrogen excess. Oop, 0.81, sorry. There we go. We need a theoretical yield, and our theoretical yield is going to be based on the limiting reactant. We had 1.23 moles of hydrogen gas. We know it's a 3:2 ratio. Based on the 3 and the 2 right there are coefficients. So the 1.23 turns into 0.82 moles of NH3 as our theoretical yield. Now, we've done moles for yields many times, but in this case, we're asked for a total volume, which means we're going to have to turn these mole amounts into volumes, and we're going to have to do that using PV equals nRT, which is kind of annoying. And if it feels frustrating at this point that we're doing the same stuff over and over, it should feel frustrating because we're doing the same stuff over and over. In fact, if PV equals nRT, we want to know our volumes now, right? Based on the assumption that these are ideal gases, and I'll show this at the end. You could just add those together, but we'll pretend I didn't know that. We know that the volume is supposed to be nRT over P. And we said in the end it's going to be 2 atmospheres and 25 degrees Celsius still. So our volume of the nitrogen is going to be the moles, which is actually let's write it. Well, 0.081 moles, 0.08206 liter atmospheres over moles Kelvin. Temperature is 298 Kelvin, and our pressure is 2 atmospheres, based on what we saw up there. We can also solve for the volume of ammonia gas that we produce, and it's going to be based on that 0.82 moles. All this other stuff is the same. Still 298 Kelvin, and still 2.0 atmospheres. Sorry, I was looking at the camera. All right, so we know for the nitrogen it's 0.99 liters of nitrogen gas, 10.02 liters of ammonia. And we can get this total volume by adding those up like we did there. And we'll see our total volume is going to be the volume of our excess nitrogen plus the volume of our NH3. And that is 0.99 liters plus 10.02 liters, which you may recognize as about 11 liters. Let me make sure that's on my screen. Good. And that is what we ended with up there. And I said, just like with the pressure one, there is one shortcut, or rather one other thing we can take into consideration. If we treat everything like an ideal gas, it doesn't matter. Hold on, my dog's barking. The type of gas, the moles don't matter, and we can just calculate it all at once. I did this at the very end of the last video. We'll put it in right here. We know V is going to be nRT over P. N doesn't matter as long as you know total moles. That's all that determines the volume. So our volume could have been total moles. RT, get ready for my dog to bark, P. And our total moles would be the 0.81 plus, sorry, 0.081 plus 0.82, which is 0.901. And so we'll do that, 0.901 moles. I'm just going to write R because I don't have room. I'm just going to write T, and it's 2 atmospheres. And we do end up, again, our volume equals 11.0 liters. It's a true story. Again, probably your fastest bet. If you can realize that when other stuff's constant, things are proportional to moles, and do then the stoichiometry with those other things, it'll save you a fair bit of time.